Welcome again. And we have a problem looking big. And piston, a spring, heating, etc. That means these are the keywords of this problem. And what is the problem? Let me read you this big statement. The figure looks good, fine. Two horizontal pipes with cross sections S and 2S. I guess S is here and 2S is here. Are hermetically, that means they are airtight. Hermetic, yeah, airtight, hermetically connected to each other. Airtight. Okay, fine. Each other and open at other ends, open at the other ends to the atmosphere. Oh, they are connected and their other ends are open to atmosphere. That's fine, I can see that. Pistons connected by a spring with a stiffness constant. A stiffness K, simply stiffness is also written. A spring constant, that is what we call it, a spring constant K, can slide in the pipes without friction. Okay, without friction, that's right. And are initially located at distance L from the junction of pipes. I guess this is the junction. Oh, there is kind of a stopper here, but they're calling me a junction. Okay, I will find what is it. From the junction of the pipes. Oh, this is certainly the junction because they are equidistant at the distance L from that particular junction, located at distances L from the junction of the pipes, and between the piston there is 1 mole of an ideal monoatomic gas. That's right. N is equal to 1. So I'm relieved from burden to writing N again and again. And at the junction there is a stopper that prevents the smaller piston moving into the pipe of larger cross section. I guessed it was the stopper earlier. Stopper, and as a result of imparting a certain amount of heat to the gas, so we have started imparting heat. Okay, heat has been given to the system, and that is enclosed between the pipes. The pistons are displaced. Okay, and that means they were initially not displacing. That means a spring was at its natural length. If there is no friction and a spring is unstretched, then only they can be at rest. Otherwise, they must have been displacing initially, and now they have displaced. That means after given a certain amount of hit, the pistons are displaced, and the length of the spring increases to 5L by 2 minus 2L. Okay, 2.5 minus 2. Half L is the extension of the spring. What will be the gas pressure between the pistons? Yeah, at this moment. By how much initially it was atmospheric pressure, if it is not stretched and they were not moving. By how much will the gas temperature change? Okay, delta T we needed to find. By what amount of heat has been supplied to the gas? Atmospheric pressure is P naught. Neglect the heat capacities of piston, springs and pipes. Thank you very much for giving, because we already assumed such things. So we are going to solve it. Understand the problem first, and then what I was telling, that since the pistons can slide freely in the pipes, so initially they were in equilibrium, and I can think that the initial equilibrium state of the system is possible only when the spring is not deformed and the initial gas pressure between the piston is equal to atmospheric pressure. So I assumed the things, and this could be true in the end. And after hitting, the gas pressure increases, of course, piston stretches, and the pistons. And what will be the next equilibrium condition? I guess the piston shift so that the smaller one rests against the stop. A stopper one comes here. Otherwise, equilibrium will not occur. So, and this length is now, length between the springs is 5L by 2. That half L is the increased length of the spring. So now I can consider, in such case, I can consider the equilibrium of this larger piston, and I can write an equation like two forces are acting on it. The spring force in this direction, so it is in equilibrium, so pressure force, so inside pressure is, suppose that P, and outside pressure is P naught, because we have been informed that the atmospheric pressure is P naught. So I can write its equilibrium equation, and it could be P minus P naught multiplied by 2S pressure per unit area, and that must be equal to half kx. No, half kx. No, I'm making a mistake. Kx. The spring force is simply kx here. So k is, new length of a spring is 5 by 2L minus 2L, and that I know is simply L by 2. So this will be KL by 2, and P minus P naught multiplied by 2S is KL by 2. And why don't I write the value of P? I can find the value of P here, and that gives us P naught plus KL by 4S. Yeah, from this equation I can get this thing. The inside pressure in this equilibrium state. And gas law, I can write the whole gas law in initial and final equilibrium states, and I'm going to write it. PV equals nRT, and initial condition, because I need to find out delta T, so I need to bring temperature somehow in the picture. So initial pressure was atmospheric pressure, I assumed P naught, and initial volume was what? I can calculate from here. This length is, this volume is SL, and this volume is 2SL. So initial pressure values are volume, pressure is P naught, volume is 2SL plus SL, and that will be, number of mole was 1. So N is gone, N is equal to 1, and this become R, and initial temperature T naught. This is my equation. And in the final equilibrium state, the pressure inside is P, and the volume is, this length is 5 by 2L. This length is 5 by 2L. And so the initially final equilibrium state, the volume is area 2S, cross-sectional area, multiplied by the length 5 by 2L, and the temperature is T. Suppose that temperature is T, so I can write like this. And I can put the value of P here. This is also a difficult task. but somehow we have got the result. So P can be supplied from here to here. You can write the value of P, and you can simply subtract 3 minus 2 and get your delta T. That is in the answer. So I can write directly the answer: delta T is equal to T minus T naught, and you will check your result will come like something like 1 upon R 2 P naught SL plus 5 by 4 KL square. If you can't find it, either you made a stupid mistake, or I did the wrong solution. Maybe anything. And now we have to find something else. We also have to find pressure. We earlier found pressure. Yes, pressure, found it. Delta T, we found it. Heat thing is needed to be found, and it can be done only by using first law of thermodynamics. You can do nothing to accept it to find the value of heat. And Q, delta U is, I guess, 3 by 2 N not N equals 1, so R delta T, and plus work done by the system. So system has worked on the surrounding. The friction has worked half K L by 2 square. L by 2 was the increased length, half kx square, the deformation in a spring, and pressure force, and the inside pressure force did the work against the outside pressure force, that is atmosphere. Big atmosphere is pressure must be constant, so I can write the value. The work done by pressure force is positive. The volume has been increased. P naught, it has worked against the pressure force P naught, so I can write P naught. And change in volume is simply, I wrote somewhere, what was the change? Yeah, the change of volume was 2s, that is 5sl minus 3sl, 2sl, and so R delta T, we have already calculated delta T, so you can put here delta T, and you can get your result. This is the result, man. This is the result, and you can get it. What was the final solution? Q, the value of Q you will find. If not, then either you are wrong or I am wrong, and there is a very little chance that I will be wrong. So the answer, it gives 5 P naught SL plus 2 KL square. And I solved this problem. I don't need to solve any more thing left in this problem. So the problem is solved. Thank you very much for watching. Keep watching.